I'm Gary Pocock, and this is my Week 12 reflection for the online modelling instruction course. This week I'm going to just sum up Unit 3 and just make a few observations that I haven't yet had the opportunity to make about some aspects of Unit 3. First thing I wanted to talk about was the drift velocity and flow rate circuit. Secondly, I just had a point to make about parallel and series circuits. And finally, I thought I'd just have a look at a PhET simulation and pass some comments on the strengths and weaknesses of the simulation in the light of the model that we've developed in the circuits unit. Okay, first of all, drift velocity and flow rate. Now, when talking about current and drift velocity, I've always felt that with my students I've done it in a fairly hand-wavy sort of way. Current is the rate of flow of charge. It's not the same thing as the velocity, and used various analogies, water flowing analogies. But I've always felt that I could do a little bit better, so I've just had a little go at writing something to see if I can clarify the concepts. Before I get to that though, this little formula here, this is taken from Charvet and Sherwood. So what we have is that the current is equal to the mobile electron density multiplied by the cross-sectional area of the wire multiplied by the average drift speed of the electrons. Okay, so in my little activity I'm going to not mention the complication of the electron density and just focus on the idea of flow rate as being a product of the cross-sectional area of the wire and also the drift velocity of the electrons. So what I did was I made up a little worksheet. Oops, that's the wrong one, it's the answer. I'll just get the actual worksheet itself. Alright, so here's my idea. Let's model the electron flow by thinking about little balls flowing through a cylindrical pipe. And we'll make our balls 1 centimeter in diameter, and we'll assume that they're moving at a constant velocity. And the question is, in each case, you have to work out what the velocity of the balls are as they're flowing through the tube, and also state the flow rate going through the tube. So we give you 2 snapshots, 1 second apart. And so we can see in question 1 here that after 1 second, one entire ball has moved across our little observation mark here. Since the balls are 1 centimeter, we can deduce that velocity is 1 centimeter per second. What's the flow rate? Well, flow rate, and again, the students must write the units down. This highlights the difference between flow rate and velocity. The flow rate is simply 1 ball passing per second. Okay, velocity and flow rate are the same in this case. But then we move on to question 2. I've just varied the velocity, and flow rate turns out to be the same as the velocity in question 2 as well. But when we get to question 3, things start to change. So now we find that the velocity is still 1 centimeter per second because the balls have only moved 1 centimeter to the right, but the flow rate has doubled because the width of the tube has doubled. And this is reinforced by more questions. Change the velocity. Velocity is 4 centimeters a second. Flow rate is 8 balls per second. Right, so we triple the width of the tube. The flow rate has tripled, even while the velocity stays the same. So students can get the idea that flow rate depends not only on the velocity, but it also depends on well, in this case I'm going two-dimensional, the width of the tube. So once they've done those questions, just reinforce the concept by getting them to choose appropriate options here. So if you keep the cross-sectional area constant but you double the velocity, then you'll double the flow rate, triple the flow rate, etc. So flow rate is directly proportional to velocity. And then if you hold the velocity constant but you double the cross-sectional area, missed the word there, then you'll also double the flow rate. So we get the idea that flow rate is dependent both on cross-sectional area and velocity. And just reinforcing that by connecting it up with the concept of current in a circuit. And then finally, let's look at what happens to flow rate when our little particles, our little balls, are going from a thick part of the circuit to a thin part of the circuit, and see how that changes things. So that's modeled here. We can see that series of snapshots. Clearly the balls are moving to the right at a velocity of 1 centimeter per second in the wide part of the tube. But when they enter the narrow part of the tube, then after 1 second the balls are moving at 3 centimeters a second. So they've had to move faster as they're going through the narrow section of the tube in order to maintain a constant flow rate. So there we have the distinction. Flow rate is the same no matter what the width of the cylinder is, but the velocity must vary. It's got to be faster in the narrow cylinder than in the wide cylinder. So, I haven't tried that on my students yet, but I will when I teach this unit next semester. And hopefully that will help them get a clearer understanding of the concept of current as flow rate and the difference between current and the drift velocity of the electrons. Alright. Now my other thought, just going back to parallel and series circuits, one of the things I've always felt students struggle with is the questions. Right? The question of why is the potential difference across parallel resistors the same, but across series resistors it changes. And it just struck me that all the work that's been done in the modelling course in Lab 1 and Lab 2 and Worksheet 1 could really put to good use here. So here is Worksheet 2, which I've already commented on. I think is a good worksheet, but it can be improved in a number of ways. And just another thing that occurred to me was that if we were to start off by actually giving open circuits like this and simply posing the question, we can put some voltage here, let's pretend it's a 6-volt battery. Simply posing the question, what is the potential difference between the open parts of the circuit? Now, the students have already measured this in Lab 1, so they will know that if it's a 6-volt battery, the potential difference from this point to this point, the open ends of the circuit, will be 6 volts. Now, if you present them with a parallel circuit that is open with 2 wire ends like this, I think it would be a fairly easy conclusion for them to draw that it would still be 6 volts across these 2 ends here and 6 volts across these 2 ends here. Once they've seen that, then slipping in some resistors into these 2 parts, it should make them much more comfortable in accepting the idea that there is a 6-volt potential drop. It must be 6 volts across this one and across this one. And if you go back to a series circuit, then it must be 6 volts from one side to the other. And if you do what I've previously suggested for worksheet 2, and create a yes. So if there's 6 volts from here to here, then there must be a partial drop in potential difference across one resistor, and then another one, a partial drop across the other one, so that they sum to a total of 6 volts. So that's just the thought I had there, that would be a useful little lead-in and to this activity, and would help students understand this rule, in inverted commas, about the potential difference in series circuits compared to parallel circuits. Alright, now my final point of discussion is about this PhET simulation. And when I look at the PhET simulations, I can't help thinking, wouldn't it be great if they could do a surface charge simulation? I'm sure it will happen one day, or someone will do it one day. The simulations are great, but I think it's early days in simulation, and I sort of imagine that in 10 years' time, the simulations that we've got now will look very primitive to what is created in the future. Now, this one, let me just play it. Alright, so we've got voltage in the battery, we've got the electrons, the drift electrons going through, we've got a resistive element with its fixed atomic cores, and we can see the collisions happening, and we can increase the voltage, and there's a temperature indicator here, so at the moment the resistor is cool. If we increase the voltage, the resisting element gets hotter as the electrons dissipate more energy in the resistor, and we can see that we've got a steady flow rate through the circuit. Okay, so this is all good. We can play with the resistance. So if we decrease the resistance, that increases the flow rate, the resistor gets hotter, so we're getting an illustration of Ohm's law, and we're also getting an illustration of the temperature resistance being affected by temperature being affected by resistance. So that's all quite good, but there are given that I know about the surface charge model, there are some real concerns about this. First of all, we know that drift velocity is actually very, very slow. That is not being conveyed so clearly here. The electrons are zipping along quite fast here. So that would, unless students are told, they could easily get the impression that the drift electrons are moving quite fast through the circuit. I didn't mention you can also reverse the voltage and get a negative voltage and it goes the other way. So very good from a macro point of view, a good way to get a feel for Ohm's law, but from a microscopic explanation point of view, as I said, I've got some concerns. Now the other major concern I had was this one. It says show voltage calculation. So if I click that, see what they're doing? They're looking here and they're counting the number of electrons coming out of the circuit here and counting the number going in here, working out the difference, and that's meant to match with the voltage here. Okay, so once we know about surface charge model, we know this is not right. The potential difference between the two ends of the battery is determined by the surface charge electrons, not by the drift electrons. So they've got clearly a wrong model